Welcome, everyone. Wow, it's really nice to see such a great group here. I'm very pleased to introduce the first in the series, our Geography Speaker Series. We will have, I believe, 4 this semester, and hopefully at least 4 next semester. We have other activities that we're working on as well. We have a distinguished guest here, but I'm going to let Dr. Bluneman do the introduction.
Yeah, actually, Mike and I thought we were both doing the introduction, so there we go, rock, paper, scissors, and decided to share the duties eventually. Dave Butler is an incredibly accomplished and kind human being, and I cannot say, I'm incredibly happy to have him here.
Thank you.
Dave earned all of his degree, bachelor's, master's, and PhD in geography. His PhD came from the University of Kansas in 1982, and it just so turns out that Mike was there at the same time. Is there anything you want to share about
What?
that time?
Rock, chalk, J.
We don't want to tell about the secret handshake or...
No.
Okay.
No.
No, I was fortunate enough. Dave and I have known each other since 1980.
Yeah.
When I arrived there, I remember the first conversation we had, you corrected me. I told you I was a PhD candidate. You said, no, you're a PhD student.
That's right. Yeah.
But I have enjoyed your company and your friendship
Thank you.
for many, many years. And as Dr. Bluneman, of course, pointed out, you are incredibly accomplished. And it's, in my estimation, I'm really proud to have come from the same school.
Thank you.
Thank you.
Yeah, so talking about the accomplishments, so I think your long video was somewhere around 65 pages long or so. And,
I don't, do I number them? I don't remember.
no, and you didn't number the publication, which made making the count really difficult. It always exceeded my mathematical capabilities. So from my count, Dave Butler has published 11 monographs, books, and edited books, which of course includes the classic Zoogeomorphology books. He was the editor of 9 journal issues. He has written, or co-written, I should say, 49 book chapters, 160 journal articles, if I got that right, I don't know. And then, of course, there are additional publications and conference proceedings. His research has been supported by a number of different agencies, the National Science Foundation, the National Park Service, Nature Conservancy, USGS, as you can see here, I decided to pull this up. I mean, there's all this published work out there that we can find online. But of course, he also has an almost daily Facebook post on Zoogeomorphology landform features. So right now we are on feature of the day number 63. And so those pictures, of course, go way back when. I think I was still a toddler, right?
Yes, probably
And
so.
what I found really interesting about the pictures, though, is that he's always waving his hand. He's always waving. What's the story behind that, Dave?
I wanted to just kind of make sure that people noticed that it was me in the picture, I think. Because, you know, otherwise I blend into the background, I guess. Honestly, I don't know. It started in 1985, I remember, because I looked at pictures from 83 and 84, and I wasn't doing it. And then in 85, there it was, and ever since. So.
Okay, so we need to make sure we get one of those pictures with you here.
Yes,
Right, before you
certainly.
leave. All right. Now, he has also, so in addition to his scholarship, I think his teaching should be mentioned. So he has served as a chair on 16 doctoral committees, on 38 master's committee, and in addition to that, he served on almost 198 by my count, other committees that you weren't chairing.
Right.
And he has received awards for teaching as well. In fact, I should point out that Dave is the Texas State University Systems Regents Professor of Geography, the University Distinguished Professor of Geography, and an honorary professor of International Studies.
Yes.
In addition to that, he's received the Career Achievement Award, something along those lines, from 3 specialty groups of the American Association of Geographers, Geomorphology, Biogeography, and Mountain Geography, which pretty much summarizes his areas of expertise. So Dave is a true physical geographer, and I'm very much looking forward to hearing everything you have to say about zoogeomorphology.
Well, thank you.
Right? Animals
is.
as geomorphic agents in the 21st century.
All right.
So, Dave,
Thank you.
impress us.
Well, thank you all for coming. I'm overwhelmed by the size of the audience here, not just how big you are, but how many there are here. I really appreciate it. I came over this morning from Cloudcroft, where I live part of the year, whenever we can, not be in the heat and humidity of Central Texas. And it's just a delight to be here today. Today I'm going to talk about zoogeomorphology, animals as geomorphic agents in the 21st century. I'm on sabbatical developmental leave this semester, as well as my wife is as well. So we are not in San Marcos this semester. We are in Cloudcroft. And I'm working on a second edition of my book on zoogeomorphology during this sabbatical time. So that's some of the material that I'll be talking about today. If you're not familiar with zoogeomorphology, it really starts with this man, Charles Darwin, who in the early 1880s published the book with the wonderful title, The Formation of Vegetable Mold Through the Action of Worms, and with observations on their habits. And in this book, Darwin, this was the last published work that he did in his life. This was after he'd been on the Beagle, returned back to England. As you can see, he was an old man at that point. And in effect, he observed the worms in his garden. And he did it for several years, and he wrote about it. He made sketches about it. He had a sketch in there of the casting of worms. This is a pic from a photograph in South India, but it looks similar to the things that he had noticed in his garden. He traveled a bit around in England after he got back. He noticed how stones at Stonehenge had sunk into the ground through the burrowing action of worms underneath some of the stones there. And so these figures are from that book that I just showed you. That was in the 1880s. The next notable work in zoogeomorphology was 100 years later. In 1988, when Heather Viles published her edited volume, Biogeomorphology, with the marvelous picture of a termite mound that for all the world looks like it's flipping the world off. And I don't know why Heather chose that photograph, but I really appreciated it very much. And the only problem with the book is that the bulk of that book is not dealing with zoogeomorphology. That book defined biogeomorphology as an approach to geomorphology which explicitly considers the role of organisms. And the book did encompass both plants and animals, but I would say 85 to 90% of the book dealt with plants, and only in passing comments on animals as geomorphic agents. And it wasn't until this book was published in 1995 that the first volume dealing with zoogeomorphology, the study of the geomorphic effects of animals, was solely devoted to the work of animals as geomorphic agents. And my interest in this came about through a seminar class in the late 1980s when I was on faculty at the University of Georgia. We were studying that semester a series of papers on the formation and failure of natural dams. And we were looking at landslide dams, glacial dams, moraine dams. And a student raised their hand in the class and asked me, what about beaver dams? And I said, I don't know anything about beaver dams, but I'll look. I'll try to find out. Next thing I was able to do was do a literature search and find out that there had been some beaver dams that had failed, that had broken out because of a heavy storm in the local area, a county over from the University of Georgia. And it killed 4 people. I thought, well, that's always interesting when people die. So we took a field trip out there to look at this site of failed beaver dams. And the next thing you know, I was hooked on looking at beavers as geomorphic agents, not just on dam failure, but on everything about beavers and the things that they do to transform the landscape. And that was in 1988, that seminar class. And then when I was on a sabbatical in 1993, I wrote the book. And because publishing took a lot longer back then in the early 1990s compared to today, it came out in the spring of 1995. This diagram, don't worry about it, there won't be a test about it, but this was a diagram that was published in a paper of mine a few years back that just shows some of the complicated things that animals do on the landscape. And I'm going to provide some photographic examples of that in a few minutes here. But basically, they do all kinds of things. They burrow on the landscape. They load slopes through the weight of their bodies if they're large enough. They dig on the landscape for food. They excavate dens. They trample the landscape, and in some cases that is a secondary geomorphic effect by producing compacted soils so that water can't get into the ground. In other cases, it's a direct form of erosion as their hooves and paws chisel into the landscape and cause surface erosion. And then, of course, over here, the separate one for beaver damming, producing ponds on the landscape, reducing stream velocity, and all the attendant things that happens associated with that. So the diversity of effects of animals on the landscape from a geomorphic perspective collectively is equal to or exceeds many of the more common geomorphic processes you study in geomorphology class. Fluvial processes, mass movement processes. Animals can be equally as or more important than any one of that group. So some examples of zoogeomorphic processes in landforms, just to give some visuals to some of those boxes on that complicated diagram. One animal that I've dealt with in one form or another throughout 30 years or more of doing research in Glacier National Park, Montana, is trying not to be killed by grizzly bears. And one time I was bluff charged by a bear, which was one of the less happy moments of my life. But I survived it, fortunately. Grizzly bears, they excavate dens and they move massive quantities of sediment doing so, and they create new dens every winter because every spring during the snowmelt period the dens collapse, so they don't reuse the same dens. They dig new ones every year. They also excavate a variety of food sources. They don't just try to eat me, they try to eat anything. Grizzly bears are omnivores, and approximately 40% of a grizzly bear's diet by volume, and this has been proven by Scat Studies, and I have the highest respect for people that do Scat Studies, because if you don't know what that is, that means that you collect their poop and you pick it apart to see what's left in the poop, indicating what they've eaten. So you'll see pieces of berries and pieces of mouse bones in the ear of a tourist or whatever the case may be. And I'm serious, they find things like that. And so 40% of a diet by volume is associated with them digging on the landscape. And to give you an indication, this is the best picture of a grizzly bear I've got. I try not to get very close to them. This is a grizzly bear paw print next to my foot. Now you can see that I'm about 6'4", and I have size 14 shoes. And that's my foot next to a paw print of a grizzly bear. And those are the front claw prints of a grizzly bear there with my 50mm lens cap for scale. So you don't want that next to you, really, but they excavate a wide variety of things on the landscape. Other animals, they're excavating the landscape for shelter, analogous somewhat to the seasonal burrows or the seasonal dens of the grizzly bears, but they live in them all year long. For example, badgers living in burrows. When I was coming down Fresnel Canyon Road out of Cloudcroft about 3 weeks ago, just on a separate side trip rather than coming down US 82, we took the side road down, and I was surprised to see there were a number of badger burrows along that road there, which I'm going to go out and take some photographs of in the near future, because they move a large quantity. Notice the apron of sediment here that illustrates the amount of material that comes out of that badger burrow. Over here, that's the burrow of a marmot. A marmot is basically a woodchuck, but in the West, they're called marmots, and there are a variety of species of marmots. This is the burrow of an Olympic marmot in Olympic National Park. That's a lens cap there, but that's my son's size 13 shoe there for scale as well. And you can see this large apron of sediment produced by the excavation of the burrows. When you start accumulating measures of that on the landscape and quantifying it on the landscape, it's an astonishingly large amount of sediment that can be moved by animals on the landscape. Just other examples from that flow chart: mound building, termites and ants. This is a termite mound in Kruger National Park in South Africa. Here's a close-up view of it, and you can see a lot of entry points and tunnels into it versus us standing there in the field. So it stood about 1.5 meters high, and it's probably 3 times that size underground. And that's a middling size termite mound. In the tropics and semi-tropics around the world, vast quantities of sediment are bioturbated and deposited on the surface by animals, if you think of them as animals, by things like termites. In central Texas, we have fire ants all over the place. If you've been following the news with Houston and the flooding in Houston, there are fire ants all over the place there that have been flooded out as well, and they're incredibly persistent. They live as floating islands in the flood right now, and all it does is, if you'll pardon the expression, is piss them off, so that when the floating islands of fire ants make ground, they attack anything in their way, and it's a very dangerous situation to encounter one of those floating fire ant mounds in the floodwaters. Trampling and wallowing on the landscape, well, particularly when something that size does the job for you. This is an elephant wallow here and here. A colleague of mine, Kevin Rogers, standing in an area where the sediment has been churned up by elephant paw print or footprints, hoof prints, whatever you call the bottom foot of an elephant. This is the pad of an elephant in the mud on the landscape, and that's my lens cap there to give you an idea of scale of the size of an individual elephant footprint on the landscape. And they churn massive amounts, and besides that, they wallow in the mud. And when you look at the elephant here, it's coated in mud, and they use that as a form of sunscreen. And it's been estimated that up to a half a cubic meter of sediment coats an elephant at any given time that they collect when the mud is available in order to protect their skin from the tropical sun. Some of the more glamorous parts of zoogeomorphology, rhinoceros urine pits. We were in the field in Kruger, and I asked our game guard, what are these unusual pits excavated on the landscape? And he said, well, that is where the rhinoceros urinates. I said, seriously? I've got to look into this. And I came home and I Googled it, and I found some videos on YouTube, and sure as heck, when they urinate, it's like a fire hose turned on, and it literally just blasts sediments out of the ground like that, and you can see it's still damp there in this particular instance here. And I thought, well, that's one that's going in the second edition, because I didn't talk about that in the first edition of the book. That's a new one on me. Then there is the avian or bird guano-induced rock dissolution, because the bird feces are very acidic, and this is from a rock just off the coast of Oregon, where much of the landscape here is being dissolved by the white material, the guano, on the landscape in this colony of cormorants. Then, tying back to the title of my talk about zoogeomorphology in the 21st century, what about human impacts on the animals? Humans have a big impact on animals in a variety of ways. We have changed the geomorphic processes in landscapes by removing native animals that had much impact. We've changed the geomorphic landscape by replacing those animals with introduced species that have strong geomorphic impacts. We changed the landscape by having human interference with the patterns of where they live, by restricting them in some places, or by allowing them to spread out in other places by reducing competition from other species that we interfere with or kill out of the area. So you think about it in the context of something like the Anthropocene, the human era. This is a really complex question. I've talked about it with Dan today and with Eric, and the issue is, would that be a good way to define it? Is looking at how we altered the geomorphic processes associated with animals. The problem is that it's time transgressive. We didn't do anything in North America until the European colonization took place. So that dates to the middle and latter part of the 1600s, really, before anything started happening in great impact. But in Europe and Asia, it took place much earlier than that. So let's take a look at some of these things. First, we're going to look at the reduction of native species that had and still have large zoogeomorphic impacts, with two examples with bison and beavers. Some of the talk will reference papers that I published on this in case that you're interested in tracking down some of the material that I've done in the past. You can go to the published literature. This is from a paper in Geomorphology in 2006, looking at how people have impacted the geomorphic landscape by changing animal populations. In this particular paper, I talked about several different species, but I'm just going to give the examples of bison and beavers here. The North American bison is a magnificent animal that weighs around 1,500 pounds for an adult male, and they were all across North America for the most part, even into the southeastern United States, in states like Georgia, when European colonization took place. There were bison in Georgia. We don't think about that, but there are place names in Georgia named after bison. There were, at best guesstimates, according to the bison biologists, 30 to 60 million bison roaming, and that was just in the North American prairie, not counting the southeast or anywhere else they lived. The effects of 60 million zoogeomorphic agents is surprisingly unquantified in the literature. The pioneers who moved across the United States on their way to Oregon and California and Washington noted in many of their journals that they recorded along the ways that areas along rivers were trampled and heavy with trails produced by the seasonal migration of the bison. And they also noticed the ubiquitous bison wallows with diameters up to several meters, which you think about, that's a big pond on the landscape. This is an example of bison wallowing and trampling in Yellowstone National Park along the Yellowstone River flowing in this direction. You notice this area here on the landscape, and I saw that on this Google Earth image, and I thought, what the devil is that weird looking stuff? And I think it was the next year I went to that site in Yellowstone. Well, the landscape is beaten to the crap by bison, wallowing and trampling in the mud along the river. And to prove that I'm not just conjecturing this, when I was standing there taking a picture, a bison started swimming across the river toward me as I stood there in the parking lot. And the bison came out of the river and emerged at the trail crossing site. And you can see, look at the depth of the incision on the landscape there relative to the size of this full-grown bison. And these areas here are incised 30 to 50 centimeters deep, and all that mud and all that material has been carried out of that environment on the coats of bison that wallow in the goo. Here is a bison in a wallow in the shortgrass prairie in Waterton Lakes National Park in Alberta, taken with a long lens because my wife wouldn't let me get any closer because I'm almost always getting yelled at to get back in the car. Whether it be in an urban environment or in a national park. One time I was out in the middle of the Champs-Élysées as the light was changing because I wanted the perfect frame of the Arch of Triumph. Get back in the car. And so, I haven't died doing it yet anyway. That's a big animal. That's a 1,500-pound animal. And look at the size of what it's created there through the wallowing. They wallow in order to coat themselves in dust and mud for protection from biting insects for the most part. Wallowing is a behavior that is employed by bison, but not by cattle typically. So the removal of bison and replacement with cattle, the argument, well, we just have cattle there now instead of bison, it doesn't wash. Bison have profound geomorphic implications that cows don't make. And the typical wallows, as reported in the biological literature, are 2 to 10 meters in diameter and up usually about a foot deep, maybe a foot and a half or even 2 feet deep. What that does in terms of the effect on the landscape, it increases the soil density, the bulk density, which is produced by their rolling and trampling, which means that the soil becomes a lot more impervious to water penetration. And indeed, one study by Macmillan showed a bulk density increase of 17% in the wallows relative to the adjacent tallgrass prairie. And that compaction reduces infiltration so that the wallows serve as local ponds. And the water can last in those ponds for several days following rainstorms. Some of the pioneers in their journals as they crossed the Great Plains noted that those were places where they were able to get water during times of passage when other places they could not find any water. If you want to start playing some geomorphic calculation games, you can calculate the amount of sediment removed out of an individual bison wallow. If you assume circularity and play with pi r square and you come up with a radius of 1 to 5 meters, since the diameter ranges in the literature are 2 to 10 meters, with a radius of 1 to 5 meters. The area of a wallow is calculated like that. Using that as an average depth, I'm not going to talk in any detail on this. An individual wallow displaces that much sediment if it's a 1 meter radius wallow, but if it's a big wallow, 5 meter radius, it can displace up to 23.5 cubic meters of sediment taken elsewhere across the plains from that site. Now, how many wallows were there? Nobody counted them, but it's been estimated off of aerial photographs and by reading the journals of pioneers and so forth, that it's well over 100 million, and that was just in the tall grass prairie alone. That doesn't include the short grass and the mid grass prairie. The ones in the tall grass prairie were estimated as covering over 80,000 hectares. And there were probably an equal combined number in the mid and short grass prairie. So think about that then in the context of the human impact on the landscape and the onset of the Anthropocene, if you will. Up until the early 1800s in the Great Plains, there were millions of bison. Within 70 years, the faucet of geomorphology was effectively turned off because there were only about 1,000 bison left by 1870 because of mass overkill. So we went from 5 to 10 million bison to 1,000. What impact did that have on the surface hydrology and runoff of the Great Plains? It's massive, and it's completely uncalculable and unquantified in the literature. One of my favorites, the beaver. I've lived with that for years, and the jokes that go with it. My mother used to laugh about it hilariously when she would go to card parties and, oh, my son studies beavers, ha ha ha. So it's like, I'm sorry, Mom. Yes, I do. That's just the way it is. This paper was published with my friend and colleague George Melanson in 2005 on beaver dams and failure of beaver dams in geomorphology. This is a photograph, not my photograph. I stole it off the web and I don't even remember where. But the beaver is the largest rodent in North America and the second largest rodent in the world after the capybara of South America. Its teeth are reinforced with iron, and that's what gives it the orange stain, and also gives it the ability to chew into wood in order to eat the wood as well as cut the wood down for construction purposes for its dams and lodges. It has webbed feet that allow it to swim well in the ponds that are produced after it builds the dams. This is the historic range of the North American beaver in effect at European contact. So before the Hudson Bay Company got going trapping the beaver. Why did the Hudson Bay Company trap beaver? To get their fur and to get their castoreum, which is a secretion out of a gland in their rear end. I don't know what they do with castoreum really. Some things I've read about say that it was used as a laxative. That sounds lovely. Some things that I've read said that they used it as the basis for perfume for women. I thought, well, good, you can use a perfume that's also a laxative. How does that sound to you? But the primary reason was fur trapping for making men's hats back in England. The hats that you see in every Jane Austen movie that Mr. Darcy's wearing and all the other gentlemen are wearing, those hats are all beaver skin hats. And that's where all the fur went. You can see here in New Mexico, there were beaver in every county in New Mexico, mostly in restricted locations like in Doñana County here. They would have been in riparian locations. Up in the Sacramento Mountains, in Cloudcroft area, they would have been in every stream up there. But there are not many of them up there now, but they're still around. How many? Well, again, who counted them? Nobody. It's estimated in the biological literature that there may have been 60 to 400 million beavers in North America at the time of contact, with I love this, the untold millions of beaver ponds. And the current population estimates in comparison, 6 to 12 million beavers in North America. Look at the factor of reduction there from 60 to 6 or from 400 to 12 million. And even at this number, at 6 to 12 million, in a lot of places we complain today about nuisance populations of beaver, where the beaver come in and dam a culvert, or the beaver come in and chew down an ornamental shrub on someone's lawn, or things of that nature. Imagine if there were 400 million beavers in North America, or even just 60 million, how much geomorphic impact that would have had prior to contact. What does the beaver dam construction do? It elevates water tables, it increases the riparian and pond habitats, it causes the water speed to slow down. If you think of it in your geomorphology text, in the context of the continuity equation, where discharge equals width, depth, and velocity, when the velocity of the stream drops because there's a dam there, discharge drops and sedimentation ensues. That means that what was a stream flowing with sediment becomes clear flowing water as the water seeps out at the base of the beaver dam. European explorers in the eastern United States reported areas with clear running streams with crystal clear sparkling water in places like Georgia, where nowadays the streams are a muddy orange color. And it's because the beaver have been removed and they're no longer there with dams sufficient to produce the sedimentation that cleaned up the water. So you have to ask yourself that question: how much has human removal of beavers changed the fluvial landscape as well as the entire biogeographic landscape, with the ponds acting as breeding habitat for any number of waterfowl and a variety of other animals as well? It's had vast influence that's almost unquantified on the landscape of North America. Excuse me. This is what the beavers like to do. They like to chew the wood down and use the wood as food or in construction purposes. This is from a book published in 1914 called The Romance of the Beaver, which is a wonderful title. It was published by A. Radcliffe Dugmore, which is another name you don't come across much anymore. Or, hey, you know, how many of you named your children Radcliffe? I didn't name our son Radcliffe. But you can see this is the original course of a stream flowing through the landscape. And once a beaver pond was created here with a secondary and tertiary dam here for extra support, how the landscape went from a clear flowing, or from a straight flowing stream to, in effect, a step pool system. And each one of those ponds acting as a settling pool, allowing the sediment to be filtered out of the stream so that when the water emerges down here, it's in effect virtually clear. The upstream pond would have the most sediment in it, but all three of those would be acting as settling ponds. This is a step pool sequence of a place we studied in Glacier Park. This is an interesting dam because we studied it in 1990 to 1994, and then in the summer of 1995, the dam failed during a thunderstorm, and we'll see the results of that here in a bit. But that fellow there, former doctoral student of mine, he's about 5'10". So that tells you something about the height of that beaver dam there. We've been out, George and I have both been out on the surface of the dam. Now I am not an insubstantially sized individual. I walk out across that thing. I've gone out on the beaver dams and literally jumped up and down on top of them just to see if I can make them budge, which the first time I did that, I thought, maybe this isn't a really good idea, because what if it does budge and the whole damn thing fails? But they never have failed underneath me yet. And you get a few sticks that crack, and that's about it. But this thing is incredibly strong. And notice how clear the water is that's emerging at the base. It just seeps out at the bottom from that pond up there, out through the base there, and the water down here is in effect crystal clear. This is an example of the sediment that's extracted from the floor of a beaver pond. It's very rich in organic matter. It smells bad because it's down from the bottom of the pond in an anaerobic environment, but all that sediment did not go downstream. It stayed in the pond. The ponds fill in over a period of time. This is one place that we looked at in 1992 and again back in 2002. In that 10-year period, the pond completely sedimented in. And it's been reported in the literature that in some places in the eastern United States, it's believed that every meadow that was encountered by European colonizers in the 16 and 1700s in the eastern forests of the United States were infilled beaver ponds. This is that same step you saw with the student standing in front of it. He was in the water right down here. This is what it looked like in 1991, an upper pond there and a lower pond here. This was in 1991, and the picture with him was 1994. The dam broke in 1995. We visited it in 1995 and then went back in 2002 to see, we were just curious, did the beaver recolonize or not? Well, they had not. What happened instead was that a nice process of succession and infilling with vegetation was taking place. This is where the student had been standing in the photograph. There's George Melanson for scale there, if you know how tall George is. I don't know, he's not very tall, but still, there's a person standing there for scale. This is the sediment that we saw in the lower pond, producing that, hey, I'm waving, how about that? In that 4-year period between 1991 and 1995, that much sediment was deposited in the pond. Some of the things you see here are subsidiary interesting features. No, those are beaver canals. The beavers dig canals in the mud in order to access bank burrows that are dug into the side of the pond back here. And I'm standing with my left foot there down in a beaver canal where the beavers would be able to go to that burrow there. And that's usually the sign of a very mature pond where the family has gotten large enough that not everybody can live in the lodge, so they send the kids off to dig burrows and live in the banks of the pond instead. We've done some calculations with ponds of known age. We know that that pond, the upper pond, was produced in 1991 and the lower pond in 1992 because we kept going back every summer over that 5-year period. So with a pond of known age, and you measure the pond, then you send the graduate student out in a wetsuit into the pond, because I'm not stupid, and have them core the pond to get the average thickness of the pond sediment. You just multiply it all together, you get the volume of sediment in the pond, then divide that by how old the pond is in years, and you get an accumulation per year. And the rates that we've come up with are in the range of anywhere from as little as 2 to up to 39 centimeters per year per pond, so over a foot of sediment per year. And this is all in a national park where there's no distinct human disturbance to the landscape in causing accelerated sedimentation to take place. So that gives you an indication of how much sediment can be trapped in a pond and how quickly. Now if you take that then and you start playing some games with, well, let's say that a pond, and we've calculated that the ponds hold 200 to 500 cubic meters of sediment. That's a lot of sediment per pond. The lower range, 200 cubic meters of sediment per pond, times 250 million beaver ponds, gives you 50 billion cubic meters of sediment in pre-European contact ponds. And nowadays, roughly 1.5 billion cubic meters of sediment that's held back from the fluvial systems flowing downstream by beaver ponds. If you use the larger range of 500 cubic centimeters per pond and the 250 million pre-contact ponds, you come up with 125 billion cubic meters of sediment were held in beaver ponds rather than flowing downstream past the ponds in pre-contact time. And that's why the settlers, the colonizers, reported on crystal clear flowing streams, because all the sediment was up in the beaver ponds. When the beavers were trapped out, the streams all flow muddy. Nowadays, if we use the upper range of 500 cubic meters and 7.7 million modern beaver ponds, we still have nearly 4 billion cubic meters of sediment per pond. So you ask yourself the question, what effect did European contact have on stream loads and water quality? Then there's the anthropogenic climate change, which we're not supposed to talk about if we're funded by the federal government. Well, too bad. In these papers, I was looking at the effect of climate change on the patterns of beaver ponds in Glacier National Parks with specific reference to beaver ponds on deltas in Glacier National Park. This is a helicopter view looking down on this particular delta here. There's a beaver pond there, one there, and there's one there. None of those three are fed by the stream. They're all fed by water leaching through hyporheic flow into the beaver ponds that you see there. That beaver pond, that set of beaver ponds in that delta was mapped by the U.S. Geological Survey as an alluvial fan. Now, if you know anything about deltas and alluvial fans, they're the shape the same, but they're very different in terms of steepness. And this photograph here on the right just illustrates that. That's an alluvial fan. That thing is at about a 20-degree angle. This is a delta. It's freaking flat. And it's a riparian environment. That's not, except right along the stream down the center of it. It makes a big difference if you're studying beaver habitat to correctly map where the beaver live. And if you map the landforms as alluvial fans, you're doing the beavers a disservice. Now you'll notice on that map, which is at a scale of 1 to 100,000, that the leftmost beaver pond is on that map. That tells you something. The USGS mapped 23 landforms that are deltas as alluvial fans, and of those, at least 9 of them have beaver ponds on them. This is another one here. This is at the head of Harrison Lake in West Central Glacier National Park, and there's a beaver pond there, 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 and there are more up here at the head of the delta as well. And so if you're trying to map beaver habitat and from that extrapolate the geomorphic effect of beavers, you first got to have an accurate habitat map. Of the 22 identified deltas in the park, of which we've so far found evidence of beaver ponds on 9 of them, all but 1 are fed by glacial meltwater. The stream that flows into this one with the 3 beaver ponds there, there, and there are fed by this stream in the hyporheic flow that reaches them, and that stream is fed by the meltwater from Red Eagle and Logan glaciers in Glacier National Park. If you know anything about the glaciers in Glacier National Park, the U.S. Geological Survey estimates that they'll be gone by 2030. What happens when the glaciers are gone? The absence of glacial contribution will lead to a reduction in stream flow to a point where insufficient flow exists to maintain adequate water in the ponds. So the ponds will get shallower, and that either means that they will freeze to the bottom, which kills the beavers, or the beavers will have to find alternative living quarters. In either event, because of climate change making the glaciers go away, these kinds of environments of beaver ponds virtually everywhere you look on the surface of this delta here will be removed. So just briefly here in the last 10 minutes or so, let's look at a few other examples of how human impact has affected zoogeomorphic patterns and amounts of sediment movement on the landscape. We've reduced the population of any number of animals, grizzly bears, from several million to about 10,000 in the continental lower 48. Prairie dogs occupy now roughly 1% of their range that they occupied at pre-contact time. Numerous other species we won't go into now. I'll show you an example of what happens with mountain goats here in just a minute, and then some final comments I'll make about things like domestication of species that have geomorphic impact, introduction of exotic species. That's a real mess. When you take an animal into an environment where it has no natural enemies and it can do a lot geomorphically, it can completely alter the landscape. Feral species, feral hogs, horses, burros, etc. And in some cases, reintroducing species. They are now reintroducing beaver into Europe. The species in Eurasia is castor fiber. It's the other animal in the castor genus in the world. There are 2, castor fiber and castor canadensis. They are reintroducing the beaver into a number of countries in northwestern Europe, most recently into England in 2015 or 16, just a year ago. And it's kind of like they're saying, we hope this will work out, even though we've now removed all the natural enemies for them. And let's put them back and hope that they'll clean the water but not make a big mess. It's like, well, good luck. It's an interesting thing. But let's take a quick look at a case known as the goat lick case, where in Glacier National Park, the National Park Service, with very well intended, what they did was the mountain goats, and there's one there and down here, they migrate seasonally in the springtime down to this natural salt lake exposed in the cut bank of the middle fork of the Flathead River. And they do that in order to ingest salt after harsh winters. Some evidence that the females do it for benefiting the babies that are going to be born. It's like a neonatal vitamin type thing, etc. And in 1979, a large snow avalanche came down and destroyed a highway bridge here. Well, why is that important? Because the mountain goats have to cross US Highway 2 here to get to the goat lick. And so when the Park Service and the Federal Highway Administration decided to rebuild the bridge across here, because this is US Highway 2, they said, let's build a goat underpass, because goats were being hit or near miss cases along US Highway 2. Speed limit through there is 45 miles an hour. There were a lot of cases of close encounters, if not downright impact and death of goats, of mountain goats. So they said, let's put in some hard-to-see fences that will guide the goats down this avalanche path, and then they'll just work their way along the side of the river to the goat lick site. It sounds great in practice. This is that site in 1983, 2 years after the bridge was completed in 1981. You can see a herd of mountain goats working along there. Even in 1983, you see a little bit of problem developing, because what they did, instead of allowing the goats to move along about a 1.5 mile stretch of road here, they made them all go down that one avalanche path. This is the goat lick site here. That's the new bridge. And this is the avalanche path that they now all have to travel down. When you fly over it in a helicopter, if you look carefully right there, you see some of the constraining fencing that they've used there and then cleverly hidden in the trees there to make the goats go down. Well, what do you see? You see this. You see that mess there. This shows a time sequence. 1994, 2000, 2007, 2010, 2012, and last year, 2016. They've taken roughly 700 goat passages per season and made them all in this one spatially constricted area. And this is the geomorphic effect, where the landscape is completely ravaged by the hooves of the goats, by the overgrazing of the goats, the excavation of day beds, because sometimes they just stop along the way during the day. Then finally, the last few topics, about 7 or 8 slides to go here. What about domesticated animals? That's a whole new thing that could be used as a marker for the Anthropocene. Well, we domesticated animals, and that's a good idea, except that they have a lot of influence on geomorphic systems. Most domesticated animals are grazing animals in one form or another. Think of cattle, sheep, goats, even camels, whatever the case may be. Studies have shown that 6 weeks of grazing by sheep on a slope with no prior terracet microrelief led to the formation of well-defined treads 30 to 320 centimeters, that is 3 meters wide, in 6 weeks. And those treads were bare of vegetation and paralleled the slope-like contour lines for up to hundreds of meters in length. And 2 weeks of grazing by a dozen cattle can do the same thing. This is a slope in Scotland. I took a picture out of the bus window I was in several years ago. These are sheep out there. All the white dots you see are sheep. And these are and up there as well. These are grazing terracets on the hillside, all produced by the weight of the sheep loading the slope and trampling the slope. Then there's the introduction of exotic species, which is never a good idea, and we've done any number of times with bad examples, the worst of which are rabbit warrens in Australia. We took rabbits to Australia because the English sailors like rabbit pie, and the rabbits got loose, and the rabbits spread across the continent with no natural enemies. And in Australia, they now occupy 30% of the agricultural and rangeland of Australia. They live in large underground colonies known as warrens. And the warrens have been studied by Dave Eldridge and his students, and they've done some really interesting studies quantifying how much sediment is moved by and excavated in a representative rabbit warren. It's up to 63 cubic meters per hectare by rabbits burrowing in a landscape where they didn't exist before. There's also interesting cases where the rabbit burrows act as karst swallow holes in the areas of Australia with enough rainfall. The rainfall falls, and instead of flowing across the landscape, it goes into the rabbit burrows, which are underlain by limestone, and it dissolves away and enters into the groundwater and never flows across the surface anymore. That was published in an interesting paper in the late 90s in Zeitschrift for Geomorphology. Then there are the feral species, where we've turned species loose. Well, we're tired of the animal, we'll let it go. Why not? Feral burros and horses. We have them here in New Mexico. They're all around the Southwest. This is out in near Red Rock Canyon Natural Area outside of Las Vegas. Aren't they cute? We couldn't hurt that. We can't do anything about that. Look how charming they are. Same with feral horses. We love horses. My friend Flicka, Fury, etc. Horses are smart, wonderful animals. We can't cull horses. Can we? Well, we should. In Australia, as well as the American rangeland, they've wreaked havoc, particularly in semi-arid to arid lands, where the landscape is kind of on an ecological tipping point. Anyway, the grazing reduces overall surface vegetation, exposes great areas to raindrop impact, surface runoff, sediment dispersal, widespread erosion by trampling. In the geomorphic literature, the effects of these feral animals, of the burros and horses, are almost completely unquantified. There's one published paper that's quantified it in the geomorphic literature for horses. Now, in some of the range management and rangeland studies, they have looked at horse enclosures, mule enclosures, and so forth, but nobody's really extrapolated it out into what about the impact they have on the fluvial systems of the American Southwest or the systems of Australia. Nobody's done it. It's a perfect PhD for somebody to go into. Then there's feral hogs, which are a big problem in central Texas. We've got feral hogs all over the place, ripping the landscape apart, trampling the landscape, rooting the landscape, digging large feeding pits and so forth. There's virtually no quantitative data available at all anywhere in the geomorphic literature on the effects of feral hogs. It's another dissertation waiting to be done.